Consider for a moment your morning commute. You start from rest, press the accelerator, and your car responds. The speedometer climbs 30, 50, 70 miles per hour. Nothing remarkable happens. No fundamental shift in the nature of reality. You're simply covering distance more quickly than before. Now imagine you could keep accelerating forever. Add more fuel, build a better engine, push harder and harder. Common sense tells us what should happen. You would simply go faster and faster without limit. After all, speed is just distance divided by time. There's no obvious ceiling written into the arithmetic, and yet the universe disagrees. Profoundly, absolutely, with something approaching cosmic stubbornness. We find ourselves confronted with a number, 299,792,458 meters per second. Light speed, the cosmic speed limit. Most people, when they hear this figure, file it away as they might file away the speed limit on a motorway. A rule, perhaps arbitrary, certainly inconvenient, probably breakable by sufficiently advanced civilizations with sufficiently powerful engines and sufficiently relaxed attitudes toward traffic regulations. This is wrong. Not merely technically wrong, but deeply, fundamentally, catastrophically wrong in a way that touches the very fabric of what reality is and how it operates. Here's the strange thing. Comparing light speed to a motorway speed limit is like comparing the rules of chess to the laws of mathematics. One is a game we invented. The other describes the structure of reasoning itself. You can change the rules of chess, allow pawns to move backward, give bishops the power to leap, and still have a playable game. You cannot change the laws of mathematics without dissolving the concept of logical consistency altogether. Light speed is of the second kind. To see why this matters, consider what happens when you break the sound barrier. An aircraft approaches that threshold, experiences turbulence, pushes through, and emerges intact on the other side. Perhaps the passengers feel rattled. Perhaps the champagne needs steadying. But the aircraft remains fundamentally an aircraft. Its wings don't shrink. Its clock doesn't slow. Its mass doesn't change. The barrier was real, but breaking it was an engineering problem. We assume, naturally, that the light barrier works the same way. Just another threshold requiring better technology. Chuck Yeager for photons. But approaching light speed, something altogether different happens. The traveller begins to change. Time slows, not the clock, but time itself. Space compresses in the direction of travel. Mass increases, making further acceleration progressively harder. You don't break through the light barrier, you transform. The barrier isn't a wall you might crash through with sufficient momentum. It's a horizon that recedes as you approach, reality itself reconfiguring to prevent your arrival. The faster you go, the more space-time distorts to keep light speed exactly the same distance ahead of you. Always unreachable. Always that same gap. The question is, why? Why should there be any limit at all? We've grown up in a universe where faster seems like it should always be available. You're travelling at 1,000 miles per hour. Add another 1,000, 1,000,000. Add another 1,000,000. The arithmetic doesn't object. The numbers don't refuse to get larger. But the universe objects. Strenuously. At 10% of light speed, time runs about 0.5% slower for you than for a stationary observer. Barely noticeable. At 90% of light speed, time runs 2.3 times slower. You might spend a year on your ship, while everyone you left behind ages more than 2 years. At 99.99% of light speed, time runs 70 times slower. A week for you nearly a year and a half for them. Notice the pattern. The relationship isn't linear, it's asymptotic, curving ever more steeply toward infinity as you approach light speed. To actually reach light speed, time would have to stop entirely. Your length in the direction of travel would contract to zero. Your mass would become infinite. These aren't engineering problems, they're logical impossibilities. You cannot accelerate an infinite mass. You cannot contract to zero length and still be a thing. You cannot experience zero time passing and still be someone to whom things happen. The universe isn't telling us we can't go fast enough. It's telling us that fast enough loses meaning as we approach light speed. The very concepts we use to think about velocity, distance, time, mass, dissolve when pushed to that limit. And this raises the question we must pursue. What is light speed really? It's not simply a large number on the same scale as other speeds. It marks something fundamental about the structure of existence. The rules don't merely restrict what we can do. They reveal what reality is. Every time you check your speedometer on a motorway, you're using concepts that work perfectly well at those modest velocities. But those same concepts, when pushed toward light speed, reveal themselves as approximations, useful shortcuts that hide a stranger truth beneath. The speed limit that isn't a speed limit at all. It's something else entirely. As we shall see, that something else turns out to be rather more interesting than any mere traffic regulation. It touches causality itself, the relationship between cause and effect that makes the universe comprehensible, and it raises questions that physics can pose but not yet answer. But first, we need to understand what experiments actually reveal about light and motion. The results are even stranger than the theory that explains them. Here is an experiment that should be impossible to describe. You're floating in space, holding a flashlight. You click it on, and light streams away from you at roughly 300,000 kilometers per second. Straightforward enough. Now your friend floats nearby, and she's also holding a flashlight. She accelerates to half the speed of light relative to you, 150,000 kilometers per second, and clicks her flashlight on while moving away. Common sense makes a clear prediction. You should see her light moving away at 300,000 plus 150,000 kilometers per second. That's 450,000 kilometers per second. Her motion should add to the light's motion, just as a ball thrown from a moving train travels faster relative to the ground than a ball thrown from a stationary position. This is not what happens. You measure her light moving at exactly 300,000 kilometers per second, the same speed as light from your own flashlight. Her velocity adds nothing. But wait, it gets stranger. From her perspective, moving at half light speed, she measures your light passing her at exactly 300,000 kilometers per second, not slower, because she's fleeing from it, not 150,000 kilometers per second, as you might expect if her motion should subtract from the light's approach. Exactly 300,000. Both of you are correct. Neither measurement is an illusion or an error. Light moves at precisely the same speed relative to everyone, regardless of how they're moving. This seems logically impossible. How can both measurements be right? To appreciate just how strange this is, imagine a rather peculiar party. Guests can only communicate by passing notes, and notes travel at walking speed about 5 kilometers per hour. A guest sitting in a chair sees notes moving past at 5 kilometers per hour. Nothing surprising there. Now imagine a guest who's walking briskly towards someone passing notes. Surely she'd measure those notes approaching faster. Her walking speed plus the note's speed. And if she walked away from the notes, she'd measure them moving slower. At this cosmic party, she doesn't. No matter how fast she walks toward the notes, away from them, sideways, notes always pass her at exactly 5 kilometers per hour. Her motion makes no difference whatsoever to the speed of the notes. This seems to violate basic arithmetic, and yet it's precisely how light behaves. The evidence for this is overwhelming. In 1887, Albert Michelson and Edward Morley performed one of the most famous experiments in physics. They reasoned that Earth moves through space at about 30 kilometers per second as it orbits the Sun. Light traveling with Earth's motion should therefore appear faster than light traveling against it, just as a swimmer moves faster with a current than against it. They built an exquisitely sensitive apparatus to detect this difference. They found nothing. Light speed was identical in all directions, regardless of Earth's motion through space. They thought they'd failed. In fact, they'd discovered something fundamental. The experiment has been repeated countless times with ever-increasing precision. The result is always the same. Light speed is constant for all observers, regardless of their motion. This isn't a measurement limitation or an experimental artifact. It's how reality works. But if this is true, if light really does travel at the same speed for everyone, then something else must change to make the mathematics work. If velocity addition doesn't apply to light, what does? The answer, as Einstein realized, is that space and time themselves must transform. Consider what we usually assume about the universe. Space is space. A fixed background, the same for everyone. Time flows uniformly, ticking at the same rate for all observers. When we measure speed, we divide a distance agreed upon by everyone, by a time also agreed upon by everyone. But if light speed is constant for all observers, these assumptions cannot all be true simultaneously. Something must give. Here's why. Imagine two observers watching the same beam of light. One is stationary. One is moving at half light speed in the direction the light travels. Both measure the light speed as 300,000 kilometers per second. For speed to be the same while motion differs, either the distance must be different for the two observers or the time must be different, or both. There's no other option. And indeed, this is exactly what happens. Space and time are not fixed, absolute backgrounds. They're dynamic, interconnected, and they transform with velocity. A moving clock runs slower than a stationary one. A moving ruler is shorter than a stationary one. These effects preserve light's constant speed at the cost of everything we thought we knew about space and time. The universe doesn't care about our intuitions. It does what the equations say. Your GPS system provides daily confirmation of this strange truth. GPS satellites orbit at about 14,000 kilometers per hour. If velocity addition worked normally for light, the signals from satellites moving toward your phone would arrive at slightly different times than signals from satellites moving away. Engineers must account for the fact that light speed is constant, regardless of satellite motion, and they must account for time dilation in the satellite clocks. If they didn't, your position would drift by about 10 kilometers per day. Every time your phone places you accurately on a map, you're witnessing experimental verification that time and space transform to preserve light's constant speed. We cannot dismiss this as illusion. We cannot explain it away. We can only accept what it reveals, that the comfortable Newtonian picture, fixed space, universal time, straightforward velocity addition, is an approximation that works well at everyday speeds but fails catastrophically as we approach light speed. The question is no longer whether light speed is truly constant. That's settled. The question is what this constancy tells us about the nature of reality. As we shall see, the answer transforms everything. Space and time aren't separate things. They're woven together into a single fabric called space-time. Motion through space affects motion through time. And at the speed of light, something rather remarkable happens. Time stops entirely. But to understand why, we need to see how the universe manages this extraordinary trick. We now arrive at the heart of the matter. How does the universe preserve light's constant speed for all observers? The answer is elegant, strange, and experimentally confirmed beyond reasonable doubt. The universe trades space for time. To understand what this means, imagine you can take exactly 10 steps per minute, total, combining any direction. If you walk entirely forward, all 10 steps carry you forward. If you angle to the right, some steps go right, fewer go forward. If you walk entirely sideways, no steps take you forward at all. Your total step budget is fixed. You can only choose how to allocate it. Now replace forward steps with motion through time and sideways steps with motion through space. Everything in the universe moves through space-time at a constant rate. We might call it light speed, through the fabric of reality. If you're sitting still in space, all your motion is through time. Time flows for you at its maximum rate. As you move faster through space, you must surrender some motion through time. Time slows down for you. At light speed through space, you would surrender all motion through time. Time would stop entirely. This isn't metaphor, it's physics. Consider a thought experiment that makes this unavoidable. Imagine a simple clock, two mirrors facing each other, with a light beam bouncing between them. Each bounce marks a tick. From the clock's perspective, sitting still with the clock, light bounces straight up and down. Simple, regular, reliable. Now watch this clock zoom past you at high speed. From your perspective, the light can't just bounce up and down. By the time it reaches the upper mirror, the clock has moved sideways. The light traces a diagonal path, longer than the straight up and down path. Here's the crux. Light travels at the same speed for you as for the clock, but your version of its path is longer. Same speed, longer distance, therefore more time per tick. The moving clock runs slow. This isn't an optical illusion. It isn't a measurement error. It isn't the clock malfunctioning. Time itself passes more slowly for the moving clock. If twin siblings parted, one remaining stationary, one travelling at high speed and returning, the travelling twin would be younger. Not because of some biological trick, but because less time would have elapsed for them. We call this time dilation, and it's been measured with extraordinary precision. Atomic clocks flown on aircraft return showing less elapsed time than identical clocks that stayed on the ground. The effect at aircraft speeds is tiny, nanoseconds, but real and measurable. At higher speeds, it becomes dramatic. At 90% of light speed, time runs at 44% of its normal rate. A year on your ship. Nearly 2.5 years for those you left behind. At 99% of light speed, time runs at about 14% of normal. A year for you, 7 for them. At 99.99% of light speed, time runs at less than 2% of normal. A week for you, a year for them. At light speed itself, the ratio goes to 0. Time stops. But time dilation is only half the story. There's also length contraction. A spaceship travelling at 90% of light speed appears compressed, squashed like an accordion in the direction of travel. to about 44% of its rest length when viewed by a stationary observer. The ship doesn't feel squashed to its occupants. Their rulers are contracted too. But from outside, the compression is real and measurable. And there's a third effect: mass increase. As objects accelerate, their resistance to further acceleration grows. At 90% of light speed, a proton's effective mass roughly doubles. At 99.99%, it increases 70-fold. At light speed, mass would become infinite. This is why reaching light speed is impossible for anything with mass. To accelerate an infinite mass would require infinite energy. The universe doesn't have infinite energy to spare. These three effects, time dilation, length contraction, mass increase, aren't separate phenomena. They're aspects of a single transformation, the reshaping of spacetime with velocity. Think back to our step budget. Everything moves through spacetime at a constant total rate. Motion through space comes at the cost of motion through time. They're the same currency, traded against each other. This is why the speed of light appears in Einstein's famous equation, E equals mc squared. That c, the speed of light, is the exchange rate between mass and energy. It tells us how much energy is locked in matter and how much mass is created when energy is concentrated. The equation isn't just about nuclear bombs and stars. It describes the deep unity of mass, energy, space, and time. Particle accelerators provide daily confirmation. At facilities like CERN, protons are boosted to 99.999991% of light speed. At this velocity, each proton's mass is 7,000 times its rest mass. The accelerators couldn't function. Without accounting for this, the beams wouldn't focus, the timing wouldn't work, the physics would fail. Every successful particle collision confirms that the universe trades space for time. That motion through one dimension affects motion through the other. That space-time is a unified fabric warped by velocity. The implications are profound. Light speed isn't a barrier you crash into. It's a horizon you can never reach because approaching it transforms the very concepts you'd use to describe arrival. At light speed, time would stop, length would vanish, mass would become infinite. You wouldn't arrive at your destination. You'd become something for which destination has no meaning. The universe is not prohibiting fast travel through some cosmic traffic regulation. It's revealing that space, time, mass, and energy are aspects of a single underlying reality. And that reality has a structure which cannot accommodate matter moving at light speed. But this raises a deeper question. We've seen what happens as we approach light speed. We haven't asked why. Why should there be a maximum speed at all? What makes light speed special? As we shall see, the answer reveals that light speed isn't about light at all. Here arrives the revelation that transforms everything we think we know. Light speed is not about light. It is the speed of causality itself, the maximum rate at which any cause, anywhere, can produce any effect, anywhere else. To see what this means, consider a simple question. When you push a domino, how does the next domino know to fall? Information about the push must travel from the first domino to the second. It moves through the material as a compression wave, propagating at some finite speed. The effect cannot happen instantaneously. Cause must reach effect through space and time. This seems obvious for dominoes. But what about fundamental forces? When the sun exerts gravitational pull on Earth, how does Earth know the sun is there? The gravitational influence must propagate through space. It cannot act instantaneously across 150 million kilometers. Even gravity needs time to travel. The question is, How fast can any influence travel? Is there a maximum rate at which causes can produce effects? The answer is yes. And that maximum rate is what we call the speed of light. But calling it that is rather like calling the ocean the whale's swimming pool, because whales happen to swim there. Technically accurate, but profoundly misleading about what's fundamental. Light travels at this speed because photons have no mass. With nothing to slow them down, they saturate the cosmic speed limit. They travel as fast as causality permits, but they don't define the limit. They merely reveal it. Consider gravitational waves. When two black holes spiral together and merge, the cataclysm sends ripples through space-time itself. Gravitational waves detected for the first time in 2015 by LIGO. These waves travel at exactly the speed of light, not because gravity is similar to light, but because gravitational waves are massless disturbances in space-time that travel at causality's maximum rate. This was confirmed spectacularly in 2017 when a neutron-star merger was detected in both gravitational waves and light simultaneously. The signals arrived at the same time after travelling 130 million light-years. Gravity and light travel at identical speeds because both travel at the speed of causality. The same is true for gluons, which hold quarks together in protons and neutrons, and any other massless entity. Everything massless travels at the same speed, not because these phenomena are related, but because that speed is the rate at which reality itself unfolds. The implications are extraordinary. The speed of light isn't derived from the properties of light. It's built into the geometry of space-time. Light happens to travel at the cosmic speed limit because photons have no mass. If light didn't exist, if our universe had no electromagnetic radiation at all, the speed limit would remain exactly the same. Calling it the speed of light is like calling the speed of sound the speed of voices, because voices happen to travel at sound speed in air. Convenient shorthand, but it obscures what's fundamental. What is fundamental is causality, the relationship between cause and effect, the structure that makes events comprehensible at all. Causality has a propagation rate. No cause can produce an effect faster than approximately 300,000 kilometers per second. This limit isn't about any particular phenomenon. It's about the fabric of space-time itself. Think about what this means. Every event in the universe sits at the center of an expanding sphere of potential influence, a light cone spreading outward at light speed. Events inside your light cone can be affected by your actions. Events outside it cannot, no matter what technology you develop or how hard you try. The light cone represents the boundary of causal influence, and it expands at exactly the speed of causality. This is why we call it the speed limit of the universe, not because some cosmic traffic authority prohibits faster travel, but because causality itself has a maximum propagation rate. You cannot travel faster than your own ability to influence events. You cannot outrun causality. And here's where it gets truly interesting. If you could somehow travel faster than light, you wouldn't merely be breaking a speed record. You'd be exceeding the rate at which cause produces effect. From certain reference frames, you'd be traveling backward in time. Effect would precede cause. This isn't science fiction speculation. It's what the mathematics of relativity demands. And it explains why the universe seems to conspire against faster-than-light travel with such determination. The universe isn't protecting a speed limit. It's protecting causality itself. But what would it actually mean to violate causality? What would happen if effect could precede cause? The answer takes us to the edge of logic itself and reveals why certain hypothetical particles, despite decades of searching, have never been found and likely never will be. Let us consider the impossible. Suppose you could send a message faster than light. What would happen? The first surprise is that the answer depends on who's watching. In your reference frame, you send a signal to a distant friend. It travels faster than light, arriving quickly. Your friend receives it and sends a reply, also faster than light. Nothing seems amiss. But now consider how this appears to a third observer moving at high speed relative to both of you. In special relativity, simultaneity is relative. Events that are simultaneous for you may not be simultaneous for someone else. This becomes dramatic at high speeds, and it creates a problem for faster-than-light signals. From the moving observer's perspective, your friend receives your message before you send it. The signal travels backward through time. This isn't a measurement error or an optical illusion. It's a mathematical consequence of relativity that's been verified countless times. If something travels faster than light, there exist valid reference frames in which it travels backward in time. And now, the paradoxes begin. Imagine you receive a message from your future self, warning you not to send a certain signal. Heeding this warning, you don't send the signal. But then the warning has no reason to be sent. So you do send the signal. So the warning is sent. So you don't. This is the grandfather paradox in its communication form. It doesn't require travelling bodily to the past and preventing your ancestors from meeting. Any faster-than-light signal can be arranged to create the same logical contradiction. The universe, it seems, has opinions about such contradictions. Every relativistic effect we've discussed, time dilation, length contraction, mass increase, conspires to prevent causality violation. It's as though reality has a chronology protection agency at work, ensuring that causes always precede their effects. This phrase isn't entirely a joke. There appears to be something fundamental about the causal structure of space-time that cannot be violated. Consider tachyons, hypothetical particles that would always travel faster than light, unable to slow down to light speed, forever on the wrong side of causality's boundary. If tachyons existed, they would carry imaginary mass, in the mathematical sense. They would require energy to slow down rather than speed up. They would, from certain reference frames, travel backward through time. Could such particles exist? The problem isn't that we haven't found them. The problem is logical. A universe containing tachyons would be a universe where effect could precede cause, where signals could travel backward in time, where paradoxes would be not merely possible, but inevitable. Consider a tachyon telephone. You receive a message from yourself tomorrow telling you to sell your stocks because the market will crash. You sell. The market crashes. You send the message. But wait, what if you receive the message and decide not to sell? Then the crash would ruin you, but you'd have no motivation to send the warning. So the warning wouldn't be sent. So you wouldn't sell. So you'd be ruined. So you'd want to send the warning if you could. But you can't send a warning about an event that only happens if the warning isn't sent. The logical structure dissolves into contradiction. This isn't a mere puzzle or brain teaser. It reveals something fundamental. Physics must be logically consistent. The universe cannot permit contradictions to exist, because contradictions aren't things. They're failures of coherent description. A universe with tachyons wouldn't be a strange universe. It would be an impossible one. And so, the universe appears to forbid them. Every attempt to construct a physical theory that permits faster-than-light travel encounters this barrier. You can write down the equations, but they produce contradictions. The theory eats itself. Science fiction, of course, is full of faster-than-light travel, warp drives, hyperspace jumps, wormholes. These aren't entirely fanciful. There are theoretical loopholes involving the geometry of space-time that might permit apparent faster-than-light travel without actually exceeding causality's limit. Wormholes, for instance, would be shortcuts through space rather than violations of the speed limit. But true faster-than-light travel, actually exceeding the rate at which causality propagates, appears to be not merely difficult, but logically impossible. The barrier isn't technological, it's conceptual. The engineering problem doesn't exist because the logical problem is insurmountable. This should fill us with wonder, not frustration. The universe protects its own coherence. Space-time bends and warps and dilates before it permits causality to be violated. The same effects that make light speed unreachable for massive objects also guarantee that cause precedes effect throughout the cosmos. What does this mean for how we understand the universe? It means that beneath all the complexity of physics, the particles, the forces, the fields, there is a deep logical structure that cannot be violated. The causal relationship between events is not merely descriptive, but constitutive. Without causality, without the orderly progression from cause to effect, the universe wouldn't make sense, because sense-making itself depends on causal relationships. We've now traced the path from common intuition, light speed as cosmic traffic regulation, to profound understanding. Light speed is the speed of causality. Exceeding it would mean exceeding logic itself. But what does this mean for how we actually experience reality? If there's no universal now, if simultaneity depends on motion, if we're each at the center of our own light cone, how should we understand our place in the cosmos? We have arrived at a truth that will transform how you see the night sky. Look up at the stars tonight. Any star will do. That pinprick of light entering your eye began its journey years ago. Decades, centuries, perhaps millennia, depending on which star you've chosen. The light from Alpha Centauri left 4.3 years ago. The light from Betelgeuse departed roughly 700 years ago during the Middle Ages. The light from the Andromeda Galaxy began its journey 2.5 million years before humans existed. This much is familiar. We understand that light takes time to travel, so we see the past when we look at distant objects. But here is the strange thing. What is that star doing right now? The question seems simple. It shouldn't be controversial. Surely there's a fact of the matter about what's happening on Betelgeuse at this very moment, even if we can't observe it for another 700 years. Relativity says otherwise. There is no universal now. The present moment is a local phenomenon. For distant events, simultaneity depends on how you're moving. To see why, imagine you and a friend both looking at that star. You're standing still on Earth. Your friend is sprinting past you at high speed, let's say, half the speed of light. An impressive sprint, to be sure, but this is a thought experiment. You might both agree that the star appears in the same location. You might agree on the light's wavelength, its intensity, all the measurable properties. But if asked, what is happening on that star right now, your answers would differ. Not because one of you is wrong, not because one measurement is more accurate than the other, because right now, for distant events, isn't absolute. It depends on your state of motion. This is the relativity of simultaneity, and it's one of the most counterintuitive consequences of Einstein's theory. Two events that are simultaneous for one observer may not be simultaneous for another observer in relative motion. Both observers are equally correct, There is no privileged frame of reference that reveals the real simultaneity. What then is objective? Causal relationships. If event A could have caused event B, meaning a signal traveling at light speed or slower could connect them, then all observers agree that A preceded B. Causality is objective. Simultaneity is not. This leads to a remarkable way of understanding spacetime, the light cone. Picture any event. Say you reading this sentence. From that event, draw lines extending into the future at the speed of light in all directions. This creates a cone in 2 spatial dimensions, or a hypercone in 3. Everything inside your future light cone could potentially be affected by you. Send a message, fire a rocket, make a decision. If the target is inside your future light cone, you can influence it. Now draw lines extending into the past at light speed. This creates your past light cone. Everything inside it could potentially have affected you. Light from distant stars, gravitational waves from colliding black holes, signals from spacecraft. If they're inside your past light cone, they could have reached you. Everything else, the vast majority of spacetime, lies in what we call elsewhere. Events in elsewhere are neither in your causal past nor your causal future. You cannot influence them. They cannot influence you. They exist in a strange limbo, causally disconnected from your present moment. And here's the key insight. Elsewhere is where the relativity of simultaneity lives. Events in your future, light cone, are objectively in your future. Events in your past light cone are objectively in your past. But events in elsewhere, whether they're happening now, depends on how you're moving. Different observers, equally valid, will disagree about the temporal relationship. What does this mean for your perception of the universe? When you look at the night sky, you're not seeing a snapshot of the cosmos at a single moment. You're seeing a collage of different times. The moon as it was 1.3 seconds ago. The sun, if it's daytime, as it was 8 minutes ago. Jupiter as it was 35 minutes ago. The nearest star beyond our sun as it was 4.3 years ago. The Andromeda Galaxy as it was 2.5 million years ago. The cosmic microwave background as it was 13.8 billion years ago. Your present moment is a tapestry woven from light that began its journey at different times, arriving simultaneously at your eyes to create the illusion of a unified now. But there is no unified now, not for the cosmos, not objectively. This might seem to dissolve something important, our intuitive sense that there's a present moment extending throughout the universe, a now that everything shares even if we can't observe it all at once. But what replaces this intuition is arguably more profound. What's real isn't simultaneity. What's real is causal structure. The light cone defines what can influence what. It establishes relationships between events that all observers agree upon. Causality, not simultaneity, is the objective structure of spacetime. And we are each at the center of our own light cone, embedded in a unique causal web, connected to some events and forever isolated from others. This is not solipsism. Other observers exist at the centers of their own light cones. Where our light cones overlap, we can communicate, interact, affect each other. The web of causality connects us even as it bounds us. Consider what it means to share a moment with someone. In everyday life, we say we're together at the same time. But what we really mean is that we're within each other's light cones, close enough that signals can travel between us effectively, instantaneously. For someone across the room, light takes about 10 nanoseconds to travel between you. For all practical purposes, you share a now. But for someone on Mars, Light takes between 3 and 22 minutes, depending on orbital positions. Your now and their now are already slipping apart. A message you send right now won't reach them for minutes. Their reply won't reach you for minutes more. You don't share a present moment in any meaningful operational sense. And for someone in the Andromeda galaxy, your light cones touch only at events millions of years in your respective pasts or futures. There is no shared now at all. The universe isn't a stage on which events play out in universal synchrony. It's a web of causal relationships, each point connected to some others and isolated from most. This is not a limitation to lament. It's a structure to understand. And understanding it changes how we see everything, including the technology in our pockets. There is a common misconception that relativity belongs to the exotic, to particle accelerators and black holes, to thought experiments and distant galaxies. Something that happens out there at extreme scales, irrelevant to daily life. This is wrong. Relativity operates everywhere, always. We simply don't notice it because the effects at everyday speeds and gravitational fields are tiny. But tiny isn't zero. And modern technology has become precise enough that ignoring relativity would cause systems to fail. The most striking example sits in your pocket. Your smartphone, when it determines your location using GPS, is performing a relativistic calculation. Without corrections for both special and general relativity, your position would drift by about 10 kilometers per day. Your navigation would be useless. Here's why. GPS works by receiving signals from at least 4 satellites simultaneously. Each satellite broadcasts its position and the precise time according to its onboard atomic clock. Your phone compares the arrival times of these signals, calculates how long each took to travel, and triangulates your position. This requires extremely accurate timekeeping. A discrepancy of just 1 microsecond translates to 300 meters of position error. The entire system depends on clocks that agree with extraordinary precision. But the satellite clocks don't agree with ground clocks, and they disagree in 2 ways. First, the satellites are moving at about 14,000 kilometers per hour relative to Earth's surface. Special relativity tells us that moving clocks run slow. This effect causes the satellite clocks to lose about 7 microseconds per day compared to ground clocks. Second, the satellites orbit at about 20,200 kilometers altitude, where Earth's gravitational field is weaker. General relativity tells us that clocks in weaker gravity run faster. This effect causes the satellite clocks to gain about 45 microseconds per day compared to ground clocks. The net effect: satellite clocks run fast by about 38 microseconds per day, every day, continuously. If engineers didn't correct for this, the positional errors would accumulate at about 10 kilometers per day. Within a week, GPS would be useless for navigation. Within a month, it would place you in the wrong city. Every time your phone accurately shows your location on a map, you're witnessing experimental confirmation that time flows at different rates depending on speed and gravitational field. Relativity isn't exotic physics happening far away. It's the infrastructure of modern civilization. But GPS is only the most familiar example. Consider particle accelerators. At the Large Hadron Collider, protons are accelerated to 99.9999991% of the speed of light. At this velocity, each proton's effective mass is 7,000 times its rest mass. The magnetic fields that steer the beams, the timing systems that bring particles into collision, the detectors that record the results all must account for relativistic effects. Without this accounting, the beams wouldn't focus. Particles wouldn't collide at the intended locations. The timing would be wrong. The entire machine, 27 kilometers of the most sophisticated technology humanity has built, would fail. Every time particle physicists announce the discovery of a new particle, they're implicitly confirming that relativity works precisely as predicted. The technology literally couldn't function otherwise. Even older technology exhibits relativistic effects. The cathode ray tubes in old televisions accelerated electrons to about 30% of the speed of light. At this velocity, the electron's mass increased enough to affect how magnetic fields deflected them. Engineers had to account for this, or the picture would have been distorted. Every time you watched an old television and saw a coherent image, you witnessed engineering that incorporated special relativity. The effects continue even in more mundane contexts. Atomic clocks at different altitudes tick at measurably different rates. Clocks at sea level run slower than clocks on mountaintops. The effect is tiny, about 1 second per 30 million years per kilometer of altitude, but measurable with modern precision. Scientists now use this effect intentionally. By measuring tiny variations in clock rates, they can map gravitational fields with exquisite sensitivity. This technique, relativistic geodesy, can detect changes in Earth's mass distribution, monitor groundwater levels, and even predict volcanic eruptions. The cosmic has become instrumental. And consider the muons, particles created when cosmic rays strike the upper atmosphere. Muons are unstable. They decay with a half-life of about 2.2 microseconds. Even travelling at nearly the speed of light, they should only travel about 660 meters before decaying. They're created at altitudes of 15 kilometers or more. They shouldn't reach the ground, but they do, abundantly. Why? Time dilation. From our perspective, the muon's internal clocks run slow because they're moving so fast. Their 2.2 microsecond lifetime stretches to tens of microseconds, giving them time to reach the surface. From the muon's perspective, the distance to the ground is length contracted, so there's less distance to travel. Either way, the muons reach us, about 10,000 per square meter per minute. You're being bombarded by relativistic confirmation right now. The physics isn't distant. It's not exotic. It's here, in your pocket, in your television, in the particles passing through your body, in the clocks that synchronize civilization. Relativity isn't something that happens elsewhere. It's something you swim in, always, whether you notice or not. But the deepest question remains. We've established what happens. Time dilates, space contracts, mass increases, causality propagates at a maximum speed. We've seen these effects in technology and experiments, but we haven't asked why. Why does causality have a speed at all? Why this particular speed? Why 299,792,458 meters per second rather than some other number? The answer, or rather our lack of one, takes us to the frontier of human knowledge. We have followed the speed of light from common misconception to profound understanding. We've seen that it isn't about light at all. It's the speed of causality, the maximum rate at which any cause can produce any effect. We've traced its consequences through space-time geometry, particle physics, and everyday technology. Now we confront a question that physics can pose but not yet answer. Why does causality have a speed at all? And why this particular speed? The number is precise. 299,792,458 meters per second. Exactly. Since 1983, The meter has been defined in terms of light speed, so the number is fixed by definition rather than measurement. But the precision of our knowledge shouldn't be confused with understanding. We know what the speed is. We don't know why it is. Consider how strange this situation is. Imagine discovering that all cooking times in the universe are multiples of 17 minutes. Boil an egg, 17 minutes. Roast a chicken, 51 minutes. Bake a cake, 34 minutes. You could describe recipes perfectly using this constant. You could predict cooking outcomes with exquisite accuracy. But you'd have no idea why 17 rather than 16 or 18. Light speed is like that, 17, except it governs everything rather than just dinner. The number appears in electromagnetism, setting the relationship between electric and magnetic fields. It appears in relativity, defining the exchange rate between space and time. It appears in quantum field theory, constraining how particles can interact. It appears everywhere physics looks, fundamental to the structure of reality. And yet, it's not derived from anything more basic. It's not the solution to an equation that might have come out differently. It's a given, a fundamental constant, a number that physics must measure rather than calculate. Some numbers in physics have this character. The gravitational constant tells us how strongly masses attract. Planck's constant sets the scale of quantum effects. The fine structure constant, which actually includes the speed of light in its definition, determines how strongly electrons interact with light. For each of these, we can ask, why this value? And for each, physics offers no answer. The numbers are what they are. Our theories use them. They don't explain them. But light speed is special, even among fundamental constants, because it's not just a parameter, it's a structural feature of space-time itself. The other constants tell us how strong various forces are. Light speed tells us something about the geometry of reality, about the relationship between cause and effect, about what it means for events to be connected at all. Understanding why light speed has its value might be tantamount to understanding why space-time exists at all. This connects to one of the deepest unsolved problems in physics, the search for quantum gravity. We have two spectacularly successful theories. General relativity describes gravity as the curvature of space-time, and it works brilliantly for planets, stars, galaxies, and the large-scale structure of the cosmos. Quantum mechanics describes matter and energy at small scales with extraordinary precision, predicting experimental results to more decimal places than any other theory in physics. But these two theories don't fit together. General relativity treats space-time as a smooth fabric that curves in response to mass and energy. Quantum mechanics treats everything as fundamentally granular, subject to uncertainty and fluctuation. Apply quantum mechanics to space-time itself, and the mathematics produces nonsense, infinite quantities, predictions that make no physical sense. A theory that unifies quantum mechanics and gravity, quantum gravity, has been sought for nearly a century. We don't yet have it. When we do, it might reveal why space-time has the structure it does, why causality propagates at the rate it does, whether these features are necessary, or whether our universe simply happened to instantiate one possibility among many. Some physicists speculate that space-time itself is emergent, not fundamental, but arising from something deeper. Just as the smooth surface of water arises from the chaotic motion of molecules, perhaps space-time arises from underlying structures we haven't yet identified. If so, the speed of light might be a feature of the emergent description rather than a fundamental law. Just as water's surface tension emerges from molecular forces and doesn't exist at the molecular level. Light speed might emerge from pre-spacetime physics and not exist at that deeper level. This remains speculation. We don't know what's beneath spacetime, or if beneath is even the right concept. The question pushes us to the edge of current understanding. But here's what makes this situation remarkable rather than frustrating. Physics has made spectacular progress by taking certain numbers as given: the speed of light, the gravitational constant, Planck's constant, and exploring their consequences. These constants define our universe. They set the rules that everything else follows. The fact that we can't yet explain them doesn't mean physics has failed. It means there's more to discover. And consider what it implies that small creatures on a minor planet can even ask such questions. We can measure the speed of causality to 9 decimal places. We can build technologies that depend on its precise value. We can trace its implications through the structure of spacetime and the behavior of matter. We can ask why this number rather than another, and recognize the question as genuinely open. This is remarkable. The universe didn't have to be comprehensible. There's no obvious reason why mathematics should describe nature, why human minds should be able to grasp cosmic structure, why the same equations that work in laboratories should work in distant galaxies billions of years ago. And yet they do. The speed of light stands as both achievement and challenge. We know it with extraordinary precision. We understand its consequences in exquisite detail. We build civilization on technologies that depend on it. And we don't know why it has the value it has. This is the frontier. Not a wall, but a horizon, with something beyond that we haven't yet reached. We return now to where we began. The morning commute, accelerating from rest, cruising through familiar streets, braking at familiar stops. Nothing seems to have changed. The physics we've explored doesn't alter the routine, and yet everything has changed. You accelerate, and in doing so, time dilates for you, by an amount too small to measure with any clock you possess, but real nonetheless. Space contracts by an even smaller amount. Your mass increases by a fraction so tiny it vanishes into unmeasurability. But the effects are there. The equations don't know about your commute's mundanity. They apply regardless. You are participating in relativistic physics right now as you read this, as you always have been, as everyone always has been. The light entering your eyes as you read these words travels at exactly the speed of causality. The electrical signals propagating through your neurons travel far slower, but they too are bounded by that cosmic speed limit. Thought is a causal process. You cannot think faster than causality permits. Consider what this means. Your perception of time passing, your sense of one moment flowing into the next, your feeling that you exist in a present moment moving forward. All of this is physics in action. The arrow of time pointing from past to future reflects the asymmetry of causality itself. You remember the past because information flowed from past events to your present brain. You don't remember the future because information cannot flow backward against causality's current. Your ability to influence the future, but not the past, is not a mere fact about memory. It's a consequence of causality's structure. Effects follow causes. You can be a cause for future effects. You cannot be a cause for past effects, not because of any practical limitation, but because the concept is incoherent. Causing the past is a contradiction in terms. You live inside a light cone. Yours, specifically. Events within your past light cone could have influenced who you are. Events within your future light cone might be influenced by what you do. Everything else, the vast majority of space-time, is elsewhere, causally disconnected from your present existence. This might seem isolating, but consider it differently. You are embedded in the causal structure of the universe. You are not an observer standing outside reality, watching it unfold. You are part of it, woven into the fabric, connected to some events and bounded from others by the same geometry that governs galaxies and photons. The speed of light that prevents you from traveling to distant stars is the same speed that ensures your thoughts have coherent order. The causality that isolates you from most of spacetime is the same causality that allows you to make plans and carry them out. The structure is not separate from you. You are an expression of it. And here is the wonder that should arrest us, that we can understand this at all. We are small creatures. Our planet is a minor world orbiting an ordinary star in an unremarkable galaxy among billions of galaxies in the observable universe. We evolved to survive in African savannas, to track prey and avoid predators, to navigate social relationships and find food and shelter. Nothing in our evolutionary history selected for the ability to comprehend space-time geometry, and yet we comprehend it. We have discovered that space and time are woven together into a single fabric. We have measured how that fabric warps with mass and velocity. We have identified the maximum speed at which causality propagates. We have traced the consequences from particle physics to cosmology, from the beginning of time to the large-scale structure of galaxies. The universe is under no obligation to make sense to us, and yet it does. The same mathematics that predicts how an apple falls predicts how galaxies rotate. The same equations that govern laboratory experiments govern stars billions of light years distant. The same speed of causality that limits our communications structures all of spacetime. There is a unity here, a coherence that we have no right to expect. Nature could have been chaotic, arbitrary, incomprehensible. It isn't. It follows laws that human minds can discover and understand. What are we to make of this? Perhaps the most profound conclusion is the simplest. The universe rewards curiosity. It reveals its structure to those who inquire carefully. It doesn't hide the speed of causality or make it inaccessible. We measured it. We understood its implications. We built technologies that depend on it. We are the universe trying to understand itself. That phrase is not mysticism, it's literal. We are made of atoms forged in stars. Our neurons fire according to the same physics that governs nebulae. When we contemplate the speed of light, we are configurations of matter using the laws of physics to understand the laws of physics. We are the cosmos examining itself from the inside. And the examination isn't complete. We don't know why causality has a speed. We don't know why that speed has the value it does. We don't know whether spacetime is fundamental or emergent. We don't know how to unify quantum mechanics with gravity. We don't know whether our universe is the only one or one among many with different fundamental constants. These questions await. Some may be answered in our lifetimes. Others may take centuries. Some may require conceptual revolutions as profound as relativity itself, shifts in understanding that make our current questions seem as naive as asking what lies north of the North Pole. But this is not cause for despair. It is cause for wonder. We began with a misconception that light speed is merely a cosmic traffic regulation, a large number on the same scale as other speeds. We now understand something far more profound. Light speed is the tempo of reality, the rate at which causality unfolds, the boundary between the possible and the impossible. We cannot exceed it, not because we lack better technology, but because exceeding it would dissolve the logical structure that makes events comprehensible at all. The universe protects its own coherence, bending space and warping time before it permits causality to uncouple. And we, small creatures that we are, have discovered this, have understood it, have built our civilization on technologies that depend on it. The heartbeat of reality continues, exactly 299,792,458 meters per second, the same everywhere, the same for everyone, the tempo that all of existence keeps. We are small creatures on a minor planet orbiting an ordinary star, but we have discovered the speed of causality itself. In doing so, we have glimpsed something of the deep logic of existence. That makes us something very special indeed. The cosmos rewards curiosity, and there is so much left to discover.